Electric field lines represent the magnitude and direction of the electric field around a specific charge distribution. The electric field of a point charge has a magnitude of E equals kq over r square, where k is Coulomb's constant. To find the direction of the electric field, we place a positive test charge. Let's place it directly above the point charge. The force exerted by the point charge on the positive test charge, in this case, is upward. So this vector represents the electric field at the location of the test charge. If you place the test charge somewhere else, also the force between them is repulsive, so the direction of the force is in this direction. So this represents the electric field at the current position of the test charge. You can repeat the same process again and again to find the electric field distribution around a positive point charge. So you can see that it is shown as radial lines radiating away from the positive point charge. Note that the direction of these lines represents the direction of the electric field, and the magnitude of the electric field is represented by the density of the lines. Note that the electric field in the area around a point charge is not uniform because it does not have a constant magnitude and direction in that area. The direction is different, and the magnitude is more closer to the point charge than it is away from the point charge. This is indicated by more field lines per unit area close to the point charge and less electric field lines per unit area away from the point charge. The same process can be repeated for a negative point charge. Now, if you place the positive test charge, the force between the point charge and the test charge is going to be attractive. So the electric field lines will look the same as the positive charge, but they will be pointing inward toward the negative point charge. The electric potential of a point charge is given by V equals kq over r, where k is again Coulomb's constant. If the charge is constant, then the electric potential depends on the distance from the charge. So at a certain distance from the point charge, you can mark several points. All of these points will have the same potential. A line connecting these points is called an equipotential line because it's a line that has the same potential. In other words, all points along this line have the same electric potential. Note that we can draw another equipotential line. In this case, the inner equipotential line has a potential greater than the outer equipotential line. You can draw several equipotential lines. In the case of a point charge, we can see that the equipotential lines look like circles. Electric field lines and equipotential lines are perpendicular to each other. Do your research to find out why. We can see this by looking at the electric field line distribution of the point charge that we just discussed. And on top of this, we can draw the equipotential line distribution of the same charge. The angle between the equipotential line and electric field line is always 90 degrees. In this experiment, you'll follow 3 steps to find the electric field lines around a charge distribution. Step number 1, you will start by marking points that have the same potential. For example, you can mark a group of points that have a potential of 1 volt or 2 volts and so on. Then you can connect these lines together. This way you can obtain the equipotential lines for this charge distribution. Finally, you can draw lines that are perpendicular to the equipotential lines, which represent the electric field lines. Because remember, the electric field lines and equipotential lines are perpendicular to each other.
This is the setup that we will use for the electric field mapping experiment. This paper contains carbon, so it's a good conductor. And the ink that we use to draw these electrodes contains silver in it, so it's a very, very good conductor. All right. Now we will take this black sheet and mount it on the side of the white paper by using two pins. Now these pins are the interface between the two electrodes, the silver electrodes, and the rest of our circuit. Notice that the pin itself does not offer a very good contact, but the best contact is obtained from this surface. So for this reason, we have to push the pins all the way in. Now the pins have to be inserted in the middle of each of the two lines and at the center sideways, in order to ensure that we have very good contact between the pins and the rest of the circuit. Now this cork board is only used to mount these pins and hold the papers in place. Now we are ready to connect our circuit, which is right here, which can be obtained from the lab manual. Now to connect this circuit, notice that these are the two electrodes. We have this line and this line connected to output number 1. This is in place of the power supply for this circuit. In order to connect a circuit like this, first of all, let's simplify the circuit. So we will ignore this connection right here and pretend that we only have these two wires, which are connected to output number 1, which is, remember, is the power supply. So in order to connect the wires to the pins, we will use a crocodile clip. All right, so we will take we'll take the red wire and connect it to one of the pins. The other side of the wire is connected to one side of output number 1. We'll pick the red side of output number 1, which is going to be the positive side. Now the other pin is connected to the other side of the power supply, which is the black side in this case. So this one is going to be the positive and the other one is going to be the negative of our circuit. Now, so we're done with this connection right here, these two wires. Now we will connect the other part. Now notice that this is connected to analog channel A, which is basically what we have here is the voltage sensor. This is called the voltage sensor. It simply measures the voltage difference between the two sides. So according to the diagram, the black side of the voltage sensor is connected to the black side of our circuit. All right? When you see something like this, a wire connected to a middle of another wire, this means that you can connect it either on this end or on the other end. All right? So in this case, because this connection here is delicate, we want to avoid making any connection here. So I'm going to take the black of the voltage sensor and connect it to the other side of this wire. So I'm going to connect it right here. Now the other wire, which is the red, is connected to an arrow. When you see an arrow, this means that this is either a pointer or something that you can change. So in this case, we will be using this pointer. So I'm going to connect it to the back of the wire. And notice one more thing. These banana plugs have a hole in the back where you can insert another wire in them. Okay. So we'll put this away in a place where nobody touches this side. And now I'm going to set up the program so that we can start collecting data for this part. The program that we will use with this interface is called Pasco Capstone. So if you double click here, now in this menu we have the hardware setup. So this is always the first step. So always you start by clicking on the hardware setup. Now we want to tell the program that we are plugging a voltage sensor to channel A. So I'm going to click on channel A. Notice that this is the same as channel A here, which is the channel where we have the voltage sensor connected. Okay, so this is a picture of the same hardware. Okay, so channel A is where we have the voltage sensor connected. So click here, and you can type V and choose the voltage sensor. Okay. Furthermore, we want to use the signal generator part of the interface, which is the power supply part. So I'm going to click on signal generator, and then here we don't need a sine wave, we need actually a DC power supply. So I'm going to choose DC, and we will set the voltage to 5 volts and select automatic. And then click on the same icon again to hide the menu. Next, we need to display the reading of this voltage sensor. Now, when we display the voltage sensor, it's better to use a digital display. So double click on digits here, and then select measurement and choose voltage. Okay. Now, change the mode from continuous to fast monitor mode. And let me maximize the screen. And then notice that when you choose automatic here in the signal generator part, when you choose automatic, this means that whenever I start recording or monitoring data, the power supply turns on automatically. And when I stop, the power supply turns off automatically. Okay, so I'm going to start monitoring here. And then I want to check my circuit. I want to test the connection between the pins and the paper. So to do this, I'm going to first touch the negative side with the pointer. And I'm supposed to get 0 or a very small number here. Okay. When I touch the other one, I should get 5 volts or a very similar number, very close number. Okay. Furthermore, the same readings should be the same on the line itself. So this number, which is very close to 0 again, should be the same as the rest of the silver line. Okay. The 4.979, which is close to 5 volts, should be the same on the silver line itself. Otherwise, if you have anything else, this means that the connection between the pins and the paper are not strong enough, and you have to push the pins harder. Okay. Now, for the first step, we want to search for points that have the same potential of 1 volt. Okay, so start by searching around. Here is 1 volt. Okay, now to mark this point, we can mark it by making a hole. Okay, then search for another point with the same potential, mark it by making another hole, search for a third point, like this one, make a third hole, and so on. So we'll repeat the process until we find a number of points that have the same potential of 1 volt. Next, we will move to the potential of 2.5 volts. Okay, so we will search for points that have a potential of 2.5 volts. I'm getting close. So anything plus or minus 0.1 volts is enough. So here is 2.59. So mark it, make another hole, and so on. Okay. So we'll repeat the same process for this group of points which have potential of 2.5 volts, and then we'll repeat it again for a potential of 4 volts. All right. So at the end, you will have a group of points that represents a potential of 1.5 volt or 1 volts. Okay. And then another group that represents 2.5 volts, and a third one that represents 4 volts. Notice that the points have to start from about 1 centimeter above the two lines to about 1 centimeters below the two lines. All right. Now, before moving to the second part, in which we have this configuration, it is very important to mark everything on the black sheet at least. So remember that this was the group of points for 1.5 volts, and this one was for 3 volts or 2.5 volts, sorry. And this one was 4 volt points, okay? So we have to write these markings, and also notice that we have to mark the location of the electrodes so we can draw them with the same dimension and the same location on the white paper as well. Okay. Now we're done with this part completely, so I'm going to disconnect it, and notice how the points that we marked are now on the white sheet. All right. So when you do this experiment, it is highly recommended that you transfer these markings to the white sheet as well. So 1.5 volt, and notice that this was the negative, this is the positive side, this here is the 2.5 volts, and this is for the 4 volt equipotential line. Okay. Now we will move to the second part. We'll do them side by side. So I'm going to mount the positive terminal inside and the negative terminal around the circle. So try to pick a point that has too much ink in it, like this one, so we have a very strong connection. Now the positive is in the middle, and we don't want the crocodile clip to interfere with our working area, so it's better to mount it like this. And the negative side goes here. The rest of the circuit remains the same. So start monitoring, and again test your connection. We have 4.97, same thing, so about 5 volts here, and we have about 0 volts on the circle. So our circuit is good, and we can start taking data. So the first group of points that we will mark are the points that have a potential of 1 volt. So let's search for 1 volt and mark it by making a very tiny hole again. Okay. So mark more points that have the same potential until you close the circle. Okay. Next, we will move to the potential of 2 volts. And again, mark a group of points that have potential of 2 volts. Okay. Again, close the circle. Notice that you will need more points, more than 10 points for the large circle, and less than that for smaller circuits. Next, I'm going to search for the 3 volt equipotential line. So mark a group of points that have a potential of 3 volts, and again complete the circle. Now if you look carefully here, you will notice that the separation between the point that had a potential of 1 volt and the point that has a potential of 2 volts, here is the separation, it is larger than the separation between the 2 volt and the 3 volt point, okay? Which means that the 1 volt equipotential line and the 2 volt equipotential line will have a separation greater than the one between the 2 volt and the 3 volt equipotential line. All right. So there is a question in the lab manual about this. Notice as a hint that the potential difference that we used between the points was always constant at 1 volt. Okay, so we moved from 1 volt to 2 volt and then to 3 volt. Now, after you're done with all of your points, do not forget to mark the location of the outer electrode so you can transfer it again to the white paper.